Hey, all right. It's talking to Shahar about using Gemini 1.5 Pro latest instead of GPT-4 for cost. Yeah. All right. Um, don't know how to see your video on LinkedIn. I'm on your page, but I don't see anything. Oh, okay. Okay, I'm in LinkedIn one as well now. Yeah. All right.
Good morning, everyone. Welcome to another week of learning. Good morning, everyone. Welcome to another week of learning deep reinforcement learning. I'm Blaze, and today we'll be discussing multi-agents and AI versus AI. This is part of HuggingFace's Deep Reinforcement Learning Unit 7. We're almost at the finish line. Uh, after this week, there's only one more unit, and we will have completed the entirety of HuggingFace's Deep Reinforcement Learning course. So, a lot of exciting stuff. I've learned so much throughout this whole process, and I can't recommend this enough. If you're interested in artificial intelligence, if you want to actually understand the underlying tech stack, a little bit of the theory, but more so applying this to your own problem set, definitely recommend it. And you're in the right place if you want to learn deep reinforcement. So let's begin. We'll start off with an introduction to what multi-agents are in AI versus AI. So this is kind of like an overview of what we covered in this course. We'll understand that transition from single agent to multi-agent systems and the significance of AI versus AI challenges. So in this video, you can see there's several players, like 2 blue bots and 2 purple bots, and they're playing soccer. This is very different than all of the environments we've learned thus far. We've done like robotic simulation environments, we've done Atari environments, and we've done the Unity environments, but not as complex as this. So some of the things to note are there is not just one agent, but now 2 agents that are on a team, but furthermore, each side has 2 agents. So some of the things to, like the terms we'll talk about is cooperative AIs as well as competitive agents. And you can see from this example, we're going to be using both. So we'll start off with single agent systems. This is something we've seen before. The concept of this is training agents in isolated environments. So all of these are the environments we've trained in previously, like I described. We had this Unity environment where the agent would go run around a map trying to find a switch that will go like spawn this pyramid, and then it has to go and crash into the pyramid. So pretty complex, not complex per se, like relatively complex to what we have learned so far, but definitely multiple steps, and there's going to be multiple like a complex reward function and a longer training time because of how much longer this is compared to what we've done before. Obviously the snowball one, where you just spawn your agent and this target will spawn in different locations. You had that cooldown and you throw a snowball, hit the target or miss, and then the target would spawn somewhere else or stay in the same place if you missed, and then you keep throwing it and try to score as many points as possible. A reminder that with reinforcement learning, we're always trying to get the highest cumulative sum of reward, and that is what we're optimizing for. And then all of these other environments we've experienced and explored throughout this course. And what the main thing that they all have in common is that they only use a single agent. So single agent systems, what they're good for in applications are they're effective for numerous tasks where interaction with other agents is not required. So kind of like a cop-out definition, but when we go to the multi-agent systems, you'll see like that is pretty much the only difference, and you add a layer of complexity to that equation. We already have that base understanding of how a single agent is trained, so we're going to be exploring what are the new considerations for the multi-agent environment. So what's a multi-agent world? This is kind of like an example is like this is how humans experience the world. Its intelligence emerges from interactions with other agents. So in the real world, there's other humans. We can think of agents as like a proxy in the digital world for humans. Since humans make decisions, reinforcement learning agents make decisions, but the environments that we've trained in are a single agent environment. But in reality, unless you're in solitary confinement, you're going to be operating with other agents, other humans that have their own reward functions, their own policy. So this is kind of getting closer to simulating that real world. And the goal with this is to create agents that adapt, collaborate, or compete with other agents. One of the examples is this autonomous agent environment. In reality, an autonomous vehicle on the road will deal with other vehicles, they'll deal with other autonomous vehicles, even pedestrians. So in the scope of just a multi-agent environment, like an example is if all of the cars are autonomous agents and they have to like operate and make sure they don't crash into each other, and that's like the main difference. Like compared to having like playing a single player game, we're now playing the multiplayer games. So, what is the importance of MARL? So, multi-agent reinforcement learning, MARL, involves multiple agents interacting in a shared environment. Some of the examples are warehouse robots and autonomous vehicles like we showed before. This is kind of like a cool image. Looks kind of, I would say maybe AI generated, maybe not, depending on which model, because like the numbers, there's like logic, F31, F32, F33, F34, that these stable diffusion or generative AI image models may not be able to replicate. But the idea is that all of these metallic robot things, they're acting autonomously, they're collaborating, and this is a real business use case. They use multi-agent reinforcement learning in some warehouses now to like save on human labor, human capital. I know like, oh no, automation is taking the jobs, but if those humans now go and do, I don't want to go into too much of a political tangent, the humans that were replaced now have an opportunity to upskill and even push further the boundary of what the human species is capable of, if they have like a growth mindset. Obviously, the situation is complex, and maybe this generalization is not the best example, but beyond the scope of this group study. If you want to talk more, let's bring this to Discord, and we can get some arguments, get some points across, and let's have a debate. Moving on. What are the types of multi-agent environments? So the main types are cooperative, competitive, and mixed. Cooperative environments are when agents work together to maximize collective benefits. An example is the warehouse robots. And in this soccer example, it's the agents that are on the same team. So the purple agents are in a cooperative environment with each other, and then the blue agent is like competing. So competitive is the other multi-agent environment. So agents aim to outperform others. They had an example in the HuggingFace course material of tennis, the tennis environment, where 1v1, the goal is to score. Like there's the rules of tennis, and your goal is to get the highest score, optimize for the greatest cumulative sum of rewards. So that's that competitive environment. And then we have a mixed multi-agent environment, which this kind of shows pretty seamlessly. We have two purple agents that are working cooperatively, but then you have the blue team and the purple team who are not cooperating. They're trying to compete. This is a mixed environment because of that, just by definition. So how do we design multi-agent systems? Decentralized systems. So what are decentralized systems? This is when each agent trains independently, treating others as part of the environment. And what's this other type? Is centralized systems. So if we have decentralized systems, we'll also have centralized systems. And this is where a central process collects experiences to learn a common policy, stabilizing the environment. So kind of the idea of over here, like everyone works independently and then treating others as part of the environment. And then for centralized, a central process collects, this is kind of like that hive mind where all of the agents are actually part of this one common policy, and that thus stabilizing the environment. There's a great YouTube video that was linked in the course called Introduction to Multi-Agent Reinforcement Learning from MATLAB Tech Talks. I went through this video and I found it like, if you're someone like me who likes to watch like animated videos that actually explain the concepts, maybe like more of a visual learner, this is a good one. It kind of shows you the robo vacuum cleaner, multiple robo vacuum cleaner example, and how it works in both the decentralized system and the centralized system. So let's go dive a little bit deeper. For decentralized systems, how are they trained? These agents are trained independently without sharing information. So one of the main drawbacks is that this is a non-stationary environment. If there is a non-stationary environment, this complicates convergence. A little bit like it'll make more sense a little bit further, but intuitively you can see that if there is like multiple, like each agent is going to be doing something to the environment, that adds a layer of complexity, so that if that other agent isn't like aware, since they are decentralized, what the other agents are doing in that environment, then that adds a layer of difficulty where it doesn't know if that was already the state, if that was the result of the agent. And these are all generalized terms. Like under the hood, we all understand that these agents are going to be, when they're trained, they're going to take random actions. They're going to optimize for those state action, like those actions in the state that lead to the maximum reward. But there's even more complexity if there's other agents changing things in the environment instead of just the agent itself. So here in the decentralized approach, we have this environment, and you can see these agents, they're not connected to each other. They will experience something from the environment. Then within them, there's like these ones, for example, use the actor-critic method, and they'll learn. There will be a buffer 1, and then thus take an action. But simultaneously and asynchronously, the other agents will be doing the same thing in the decentralized system. Now for a centralized system, the training has shared experience buffer that collects data from all agents. And the benefit to the centralized system is that it's more stable environments, and agents are treated as a larger entity. So like it sounds like, oh, maybe if everything's centralized, this will make everything better, but it's not all of these multi-agent systems can be centralized. Like you can see that how do you go and share experience? That's a difficulty. Like if you're operating in areas that can't send signal or send quote unquote messages to the other agents, then you literally are unable to operate in a centralized system. With a centralized system as part of your multi-agent reinforcement learning framework. So here, the main difference is that parameter sharing between the agents in this like dash line, and it's due to this experience buffer. So experience comes from the environment, and the agent experiences an experience from the environment, and then there's this shared experience buffer that all of the agents will pass on their experience to that experience buffer, which can be sampled and retrieved from the other agents, thus able to share these parameters and their experiences, and like simplify the collaborative multi-agentness of that environment. So one of the main concepts for this week was the self-play technique. This is when agents train against copies of themselves. So over here in this environment, throughout the training process for the soccer environment, you're going to be playing with the old copies, like the old policy from previous training runs. And that'll add everything that you can think of. Like it'll add more parameters that you're going to have to add to your training runs. There's going to be more things that you got to tweak, more parameters to change. But what this allows is that each time, like if you think about the example is like children's soccer. You don't want a child playing against a pro soccer team. You want the child to play against other players, maybe the same physicality, same skill level, because that is the most conducive to learning. If you put the child and play against the pros, they're absolutely never going to win. That agent is never going to get a reward because the other agent is just too good. And the way to go about this is this self-play concept where you're going to be training against yourself. You're going to be battling your own demons. You're going to be battling your previous self, your last save, and continually iterating upon that. So the benefits is ensuring opponents are at a comparable skill level, facilitating gradual improvement. So an example is like you'll train against like exact copies of yourself for maybe 10 runs. You'll update your policy, update reward function, and then play against that last saved copy with the goal of trying to score and then thus increasing your reward, updating your policy as you go. and then repeating that process as a loop until you get to your desired outcome or the desired training time steps that you have set for your experiment. So the course talks a little bit about the historical use of self-play. There's this example of Arthur Samuel's checker player, TD Gammon, that's listed in the course material, and that's like a historical example, but the modern use case is that this self-play concept is integrated into the ML Agents library. And they linked inside of the coursework this nice article for those that are interested. It's called Training Intelligent Adversaries Using Self-Play with ML Agents. So this is a Unity article, and it talks a little bit more about the background and how this was all came about, because like we're operating in this Unity environment, we're using the ML Agents library. It started from somewhere, so for those that are interested more in the history, I'd recommend you take a look at that. So one of the other ideas, concepts that's introduced to us is this ELO score for evaluation. So maybe you played chess, maybe you've played like League of Legends or any other competitive game where you get like this score, this rating, and that's the same concept here in reinforcement learning. So the purpose of this ELO rating is it measures relative skill levels in a zero-sum game. So in like chess, there could be one winner, and then that winner plays against someone, and they both have these ELO ratings. And at the end of the game, there's going to be one winner. Maybe it's a draw, but to make it easy, let's just say that there's someone won. And what happens, like high level, is that the winner is going to take points from the loser's score and then add it to their own rating. But there's this formula that is depicted here for how that's done. So the calculation is based on match outcomes and opponent ratings. So maybe there's ELO player 1, player A, and player B. This is how you get their ELO. And so like in chess, like everyone starts at 1200, and then you keep playing games, you add to your score. And the idea is that if you have a high ELO and you go against someone that has a lower ELO, you're not going to gain much points in your own score because of that huge gap in skill level. And however, if you're much lower than the higher player, like say you're like at 1200 versus a grandmaster at like 2400, and you win, your ELO is going to go up significantly, their ELO is going to go down significantly. And then the closer you are together, the more like even that difference in change is going to be. But if you think about it, what we're trying to accomplish in this multi-agent reinforcement learning and with self-play is kind of like trying to increase our ELO level. So every time your agent plays, you'll have an ELO score. And obviously you want to optimize for a higher reward, and this is like a way to do that, like to get a numerical value from that. So this is the concept of ELO is how we're going to evaluate in this training run for today. So that concluded the coursework of the multi-agent reinforcement learning AI versus AI section. And like I'll reiterate that this is a introduction. So there's definitely a lot more to cover, but this covers like what we've gone through so far is the majority of that high level stuff, the main concepts, and I try to explain it as simply as possible. So I will preface that I tried to get my training runs going for this ML Agents, the soccer environment. I did the big no-no is trying to test in a different environment. I usually test in Windows, but I wanted to try in my WSL instance, but still have difficulty with my environment within WSL and conflicting like packages. So I would say if you have trained on your own before, make sure you just stick to the environment that you know. I like to do all my web development, software, like coding stuff, specifically for like web applications, since the servers that you host everything in are generally Linux based. So I wanted to replicate that with this training run, but could not figure it out. Like I started it like last night, this morning, so more to follow. But I'd recommend stick into the environment that you know before you try new stuff. So how you get set up is obviously the environment is going to be Soccer 2s, which is a 2v2 soccer game. There's going to be a config file which defines the hyperparameters for training, and this time they don't recommend using the Google Colab because of timeout errors. The training should take between 4 to 8 hours, so they recommend using your local for this. So I started going down the process. You can copy a bunch of the code from the actual instructions. So the process remains the same. We're going to go get our environment set up, go get our Conda environment, make sure that we're operating in this RL or whichever virtual environment that you want to use. And then get your dependencies, install everything, navigate to the right directories. You get the gist of it. And then from there, there's a hyperparameter file. You can go edit that based on your own liking. And then once you have your hyperparameters set up, you go and train your agent. So you'll use this ml-agent-learn command with parameters that you'll pass. You can pass like the path where the hyperparameter config is, the environment, pass the environment, where the environment executable is. This is something you'll download while you're working through the material. Give a name to your training run, and then launch the no graphics decorator to ensure that you don't use like unnecessary GPU while you're training, or else that'll take up more time and might not even work depending on the hardware you're using. They claim that you can use like a pretty like standard laptop to get this done, but it depends on, takes 4 to 8 hours depending on your hardware. So that's a consideration. This is the part where I still have to get to. I have to complete my training run, but covered all the course materials so far. So after you train your model, you can push it to HuggingFace Hub. And what's cool is that you can go and compete against the other people in the course, see who has the best soccer playing agents, which is pretty cool stuff. So that's what the visualization is. You can view matches to assess agent performance, and then you can look at the demo space here. You can take a look quickly. Before we do, the key takeaways from this week's unit are the transition from single agent to multi-agent systems. There's going to be more parameters since this is going to be a more complex environment. There's a few different training approaches. There's that decentralized versus centralized approach. This idea of self-play, so you can get better by playing against yourself, like your old training runs, and this is effective for competitive agents. And evaluation is done through this ELO rating system. So we can go take a look at some example models. I'll just look at this guy versus this thing, and at the end of the game, you can see these agents. Like sometimes it's really funny depending on how much training they did. It looks like these agents are very scared of the ball. Maybe experiencing some social anxiety. Maybe they need a pep talk from mom and dad to go tell them, believe in yourself, son. Go ahead, get the ball, be aggressive. But it's kind of funny, like anthroposizing these AI agents. And on the content side, since if you're not familiar with me, I like to, like, I'm an aspiring YouTube creator. Haven't gotten a big YouTube channel yet, but some of the big reinforcement learning channels, they kind of make a nice story out of training their AI agents, because every time you start off, the AI agent's going to suck. It's going to do random actions, never going to play the game right. And like over time, like you improve yourself, you face adversity, you train against your previous copies of yourself if you're using that self-play concept, and then you get better. And those videos are getting like millions and millions of views. There's one specifically for the Pokemon environment, where this guy made the story of like, oh yeah, like you just imagine you're like in third grade again, playing Pokemon Red for the first time, pulling out your Game Boy, and then not knowing how to really play Pokemon and just doing random actions, which is exactly what the AI agent's going to do when it does the first training runs. So, yeah, don't want to belabor a point. Looks like they're not going to really touch the ball. Okay, looks like they gave up. Let's find one that's actually going to win. I'm just going to keep going to the middle. Okay, this guy. Oh, okay, there we go. This one, the blue team really understands how to play. Wow, they're dominating. Wow. This is like pretty interesting. Like the purple team probably didn't train enough, or they need to go back to the drawing board with their config file, update the parameters to something that works. Try to put in more courage in their parameters. I'm joking when I say all this stuff, but it's just funny to think, like, imagine if this was a little humans playing. But with that, yeah, do we have any questions?
Not really a question, but you should really like show off the robots that actually play soccer and how this is like very close to how you would just train like a virtual
Yeah.
like soccer player, and then you can just immediately put it into the robots. I have like here, I'll send it to you.
Yeah, I know what you're talking about. That's actually really cool. That's like the stuff that I want to do. That would be real complex if you think about it, because you not only do you have to teach the AIs how to walk, that's like it's a challenge in and of itself. You got to go and like, yeah, there's a simulation. You have to go take it from that simulated world, like that game environment, and then bring it to the real world. And you can see that even just like standing up and balancing is hard. These guys are having like seizures, which is basically what the purple team is doing over here. And then, wow, look at that. They get real good. They're like now able to, they got agility. They can, 5 years of training. That's crazy. And yeah, this research paper came out in 2022 too. So this is like, these findings came out like 2 years ago. This is pretty cutting edge stuff. And like, I know LLMs get a bunch of hype, but there's definitely like, with more compute, with quantum computing, these training runs for deep reinforcement learning are going to be so much faster. This is so advanced. Advanced relative to what I know right now. So yeah, it's a cool example. We're now at the 33-minute mark, so we can go and call it good. Make sure you come check us out again next Thursday, 10 a.m. Eastern, for the final section. We'll be kind of deliberating over what we'll be covering next after this. But if you've been working through the course with me, we'll be getting our training certificates. And if you get a passing score on all of them, you'll get the HuggingFace Certificate of Honors for completing the deep reinforcement learning. So if you want to have extra reward and optimize for a higher cumulative professional satisfaction, make sure you go and get 100% passing on all of the different training environments that the course is forcing you to train in. And if you have any questions, feel free to message on Discord. Let's keep this chat going. And with that, have a good day. See you next week.